architecture, and I'm sorry, I see I'm running late. I'll try to go through this super quickly so that we don't push back the next speaker. But big data requires massive compute. Small data now, with customers I work with, is a few terabytes. Oh, you use small data, you've got 5 terabytes. Dozens and hundreds of terabytes going to petabytes, going to whatever. That's the kind of data that we're going to see in the future in our data lakes. And so the challenge is that to train that data on these massive models requires incredibly huge, literally supercompute power. And so the problem is that, okay, Moore's law is, as we all know, is rolling over now. But we all know as well that starting back at 65 nanometers, you couldn't crank up the clock speed indefinitely. So the single-threaded performance started rolling over. It's that lower blue curve way before Moore's law started flattening out. So what that implies is that you have to go to a parallel compute architecture. And I had a nice video that I'm going to skip for time, but that shows how an NVIDIA GPU has typically 3,000 to 5,000 parallel cores, and not for every operation, but for numerically intensive operations, those 5,000 cores are something on the order of 100 times faster than a CPU that might have 10, 20, 50 parallel cores if you have a dual socket machine. And so I'm going to skip this video. And what's happening is that, so you have the potential with graphics processing units, which came from the world of video. We've repurposed them to be general computing machines. That's what we do at NVIDIA. And we have a language called CUDA, which allows the deep learning framework programmers to easily leverage these parallel computing cores. And so the good news is that even though Moore's law is shallowing and single-threaded performance already was shallowing, we've still got a lot of juice left to squeeze in this lemon to make some sweet lemonade, because you see that the CPU performance is scaling very weakly. Now, both in compute power and memory bandwidth, the green line is the GPU compute power in flops and memory bandwidth. And so what you need is typically, if you would have tried to do something like deep learning, machine learning, or complicated data analytics, you would typically scale out to a large cluster, maybe something like a Spark cluster. But nowadays, people that are using these deep neural networks, they don't necessarily want to scale out to a large cluster. They can scale up to a dense GPU node server that might have 8 GPUs in it. And because it doesn't have to talk over the network, it has high-speed interconnects within the same box. You can use those 5,000 cores on every GPU, and they can communicate efficiently. And what you get is quite remarkable. So we've built, and I guess this is the sales pitch of this, of this talk, but we built a custom-built supercomputer. It's a 3U server with 8 of our latest GPUs, and this box, called the DGX-1, is equivalent to, it's faster than 128 Knights Landing servers when you benchmark it on an image recognition, deep neural and network and other neural network benchmarks. And beyond just raw supercompute power, it has a fully integrated software stack where all of the deep learning frameworks are containerized, and you can download them from software registries. So everything you need as an enterprise to have your data science team be productive. And that one box, that's a 3U server, that's more powerful than the most powerful supercomputer in the world was in 2004. It was something called the Earth Simulator in Tokyo. It had its own building, and it was a $2 billion supercomputer, #1 in the world. This thing is more powerful. That's a 3U server. So it's really remarkable the power that you get, and this is exactly what's needed to train these deep neural networks. I'll just make this the last slide because I do apologize, I'm running late. But we asked ourselves, well, if this one box is equal to the most powerful supercomputer in 2004 and 128 state-of-the-art data center servers now, what would happen if you plugged 128 of these boxes together? If you really needed power to crank through deep learning, well, we did it, because we're NVIDIA, and we have them, and we plugged them together with high-performance computing fiber optics. Within each box, there are these very high-speed links that are faster, called NVLink, faster than PCIe Express, and you immediately get I hope I'm not misquoting this, it's the 26th or the 28th most powerful supercomputer in the world on the top 500 list. It was #1 on the Green 500 list, and we're using it for deep learning research. There's a deep learning framework just for cancer that mixes HPC molecular dynamics and deep learning. And by the way, if you only plug 13 of these DGX together, you'd already get onto the top 500 list. And so we have the power, we have the data in our Hadoop data lakes and our databases, and we have the algorithms. So the next 50 years is going to be about this.